Yeah, today we have Dr. Wanliang Shan. Dr. Shan actually was actually a classmate of mine in Princeton. He obtained his PhD at Princeton in mechanical engineering, and then he spent some year at Carnegie Mellon to do a postdoc, mainly focusing on developing smart materials for soft robotic applications. He's now assistant professor at Syracuse University, and before that he was assistant professor at University of Nevada, Reno. So his expertise is mainly combining mechanics and materials and soft robotics to develop these very wonderful multifunctional materials, high performance smart materials for soft robotic applications, and which actually a lot of interesting material design. So today he's going to talk a lot about this interesting work.
Okay, yeah, thank you, Yang, for the nice introduction. Yeah, I guess I need to share the screen, right? Somehow, I don't know who is the host. Can I share the screen? Oh, I can, I guess. Okay, I can share the screen. Yeah, I'm gonna share the screen. Yes. Right, can you guys see my screen?
Yes, we can see your screen.
For a second, I guess. Yeah. Okay, great. Once again, thank you for the introduction, Yang. And today is my great honor to talk about my research at ASU. And my title is Integrating Smart Materials and Solid Mechanics for Soft Robotics. There's three keywords there: smart materials, solid mechanics, and soft robotics. But the focus actually will be robotics. So now when we talk about robotics, the first thing coming to mind might be this gigantic one that can be found at the manufacturing lines. These are typically fixed to the ground, and they can do their task pretty accurately, and they do heavy lifting duties like picking up car parts, right? The field of robotics have been growing really fast, and now it has expanded into this topic of biomedical devices and wearable devices, such as this robotic needle for suturing applications, and also this drug-eluting stent for heart disease treatment, as well as this shoulder exoskeleton for human motion assistance. From the left to the right, we can see that actually there are more and more machine environment interactions involved. In particular, there are more and more human machine interactions involved as robots, right, keep invading our daily life, including hospitals and kitchens, etc. So exactly because of this more and more human machine interactions, there has been a surge of soft robotic research in the last decade. This starts back in 2011. There's soft crawling robots being reported from a group at Harvard. And then there's also this modular soft gripper in the middle here. And more recently, actually, there's this soft robotic glove for rehabilitating purpose. I think probably Geronos actually was at ASU at least a couple of years ago. So when we talk about soft robotics, and when we compare the soft robotic with traditional robotic, actually, there are a lot of advantages. In particular, these include better adaptability to unexpected environments, and coming with that will be safer human-machine interactions. Of course, there are also challenges. For example, they are typically less precise when compared with rigid counterparts, and also they are harder to control, especially due to the non-trivial dynamic modeling part. Another thing is there are less available sensors and actuators on the market. You try to assemble these software machines. This is all opportunity for us as a researcher, I will see. So when we look at our human body and robotic, right, we kind of emphasize this trend from shifting from like a in factory to our daily places humans reside, right? So when we compare humans and robots, we can quickly realize actually they're made of materials from sitting from this two extreme end of this modular spectrum. So traditional body, they use metals and hard plastic and silicon, whereas our human body are typically made of muscles, tissues, etc. They're soft and squishy. But if we examine more closely, we also notice actually our human body is not purely soft. Unlike some sea creature, right? We know there are some of them actually are purely like octopus. They're purely soft. But our human body actually are not purely soft. We also have bones actually. Here you can see bone actually sits at also this end of the spectrum here. So we kind of and if we look at our human muscle, right, there we also realize they can stiffen and relax when needed to perform all sorts of tasks. So hereby we identified this grand challenge, which is design of small materials with tunable stiffness for better human machine and environment interactions. And recently there's this also this is fitting into the big theme of physical artificial intelligence. We know that actually artificial intelligence has been popular, very popular in the last I would say 5 or 6 years. Especially on the software side, right? But there's also this physical AI thing, people have been spending a lot of effort on, which is what we're trying to do here. So with that, I'm going to introduce the research theme of my group, which is smart, hybrid, active, and nature-inspired materials, mechanics, and machines. So literally in the middle of this thing, this is the focus of my group. I actually started with this solid mechanics background, and also started working on small materials in my postdoc years. And eventually we're trying to develop all sorts of hybrid and soft robotic devices, which I will talk about in this seminar. This is the kind of the blueprint for my research program. Our ultimate goal is to try to improve the human-machine environment interactions. And we can divide the efforts into two groups, which hardware or software, or we can call it physical AI and also virtual AI, if I put it. And these include wearable devices, medical devices, soft robotics, and also AI, the AI we are familiar with. So and eventually these will be built on fundamental areas including thermal science, materials engineering, and solid mechanics, as well as machine learning and computer vision. These are more like CS concepts or topics or areas. So with that, I kind of set up the background for my research and also the motivation for that. Next, we're going to look at one topic, which is compliant robotic manipulation. We do this by integrating small materials and relevant mechanics. I'll kind of elaborate on those topics. We'll first look at recent studies on this, soft grippers, and kind of identify their limitations. We then go over 3 relevant designs of soft grippers by my group. And in the end of this section, we'll do a quick summary and also provide an outlook on future work on this topic. Well, the first approach actually, first approach for soft grippers, they're based on pneumatics. So here, there's a modular soft gripper, which I showed earlier. This gripper has multiple fingers. They are all controlled by one air input, one channel. And when you inflate or deflate this, the pressure of these channels or chambers, these individual fingers can bend inwards or stretch or expand. So that way, collectively, the gripper can do grasping and releasing manipulations. So here there's another example, which mimics elephant trunk. So here it might not that be clear, but here there's a piece of rock actually. As you can see, this structure is made of rubber, and it has a flexible outer shell. And this shell actually is filled with incompressible liquid. There are also 2 quasi-longitudinal cables that can be used to help generate this bending motion. And this is kind of heavy duty because you can pick up that big of piece of rock. This approach is based on jamming of granular materials. Once again, it's all pneumatics actually. The trick is, you start with a balloon of coffee dust or something. So these are granular material. When there's air inside this balloon, the granular material can loosely move around, and they can such that when the gripper is gripper approach this all sorts of objects, they can engage much better. And then once after engaging, you can take out the air out of this balloon, and then the granular material will stiffen. They cannot move freely anymore, and that way they can pick up objects with weird shapes, such as this one. This is more like a cylinder. The last example, actually, here, as you can see, actually, they combines both jamming of granular materials and also tension cables to do a more sophisticated thing. This gripper here has multiple segments. Another approach for compliant gripping is based on electro-adhesion. So here I have one recent paper coming out 4 years ago, actually. In this soft gripper, actually, there are 2 fingers, and each finger actually is made of this 5-layer structure. So you start with some pre-stretched elastomer layer in the middle, and then you can attach electrodes on top and bottom, and you can do the sealing layer top and bottom. The pre-stretched layer will be released, right? Once you don't hold on to that pre-stretched. And then the result is this soft finger here. They will be naturally in this curved geometry. And then when you apply high voltage across this very thin layer of dielectric elastomer, then this, because of the strong electric field, this is going to extend again. And that way, actually, you can see the finger will straighten, and collectively these 2 fingers will generate this closing up or grasping motion. Now, closing up is just one part of this mechanism. Actually, they're applying high voltage, and then there's an electric field close by, and there will be electro-adhesion between the object and each finger. That way, actually, they were able to pick up all sorts of objects, including this chicken here, and I believe this is a kind of a peeled grape or some other fruit. And there's also senator, and this is the envelope, and there's the I guess small can something. Now, these are actually not only this. Actually, I went to this company called Grabit in the Silicon Valley. They actually have been using electro-adhesion to manipulate fabrics. Here, there's a charter, right? But they also built custom designed equipment to handle the shoe layers, for the sneakers we wear. So they're especially those from Nike, right? Actually, they did a contract with Nike. So there are multiple layers, and they use electro-adhesion to manipulate those layers and try to optimize that process. The last approach I'm going to talk for soft grippers is based on tunable dry adhesion. So these are mostly gecko-inspired dry adhesives, and for this topic, actually, Professor Manicity and also Professor Alfred Crosby, they have been contributing significantly to this topic. So people actually, scientists have been looking at the mechanism and the underlying dry adhesion for gecko's fate. They found out actually there is a multi-scale hierarchical structure that are responsible for the strong dry adhesion. People, so researchers have been mimicking gecko's foot, and they have built this array of fibers with tapes. And also this one is kind of tilted, array of tilted fibers to achieve directional dry adhesives. Kind of more recently, Professor Kevin Turner at Penn come up with this approach. They argue that actually, if you replace the core, if you insert a rigid core into otherwise homogeneous elastomeric post, you can actually alter the stress distribution on the interface, and that way you can alter the dry adhesion. They did both experiments and also finite element. They were able to kind of identify the mechanism for the switch of dry adhesion. Basically, actually, if you don't have the core, you're going to have a stress concentration here at this corner, and clearly you're going to have an edge crack. But if you have the core, you're going to alter the stress distribution, and the crack will more likely be happening here. So they have this critical parameter T over R here, which is the x-axis in this plot. When you change this T, you're gonna change the alter the stress distribution on the interface, and that the mechanism I described will kick in, and that will be responsible for the increase of dry adhesion of the structure. Well, these are very good, but they have common drawbacks. We talk about 3 approaches: pneumatic approach, electro-adhesion approach, and also dry adhesion approach, right? The existing dry adhesion approach. Now, none of these grippers functionality actually can be actively tuned once fabricated. It's once and for all thing. You cannot dynamically change their functionality, and none of the grippers can generate twisting motion. They mostly doing grasping, and they stop there. Now, I wouldn't say that actually it's not that they cannot do. For example, the pneumatic ones, they can do twisting, but using their approach, it will be very complicated because if you want to control each finger, they will need multiple channels, and they will need many controllers or many pumps, like pressure controllers, all the things. It's very complicated, and that's the reason why they didn't do it. So another one is none of these grippers actually have individually controllable fingers, which I just touched on. If they want to do that, it will be challenging. It's not impossible. It will be challenging. It will be complicated for fabrication and also for control, etc. So for the tunable dry adhesion approach, the tuning is mostly static. So we show some example of gecko inspired dry adhesive. So as you can tell, there's no dynamic mechanism to control the dry adhesion. You have to do some maneuver of the loading direction, etc., right, from the arm point of view, and so there's no dynamic changing in the material, in the adhesive itself. So our goal here on robotic manipulation is to design soft end fetters that can be actively tuned, can generate twisting motion, and can manipulate objects much larger than their own sizes towards the ultimate goal of universal manipulation. We achieve this by integrating smart materials and random mechanics in the grip design. So the first approach I'm going to talk about by my group is a new multi-finger soft gripper. So for this gripper, as you can see here, we're going to have 3 fingers, whereas each finger is made of these multiple segments. Judging from the color, you can see there are 3 different components. I would see the whitish thing is the PDMS, which is relatively rigid. And here for the joints, we have EcoFlex. We have 2 EcoFlex joints, which can inflate if you change the pressure of this shared hollow chamber here, which I cannot show it, but just assume there's a chamber actually all across this multiple components. And on the side of wall of this finger, there's multiple we call it ligaments, which are made of small materials. And then when we can selectively activate these ligaments, soften or rigid, right? Make it rigid. Then that way we can generate manipulation. So to put this in a schematic, so this is the top view of the 3 fingers. The grain position, as you can tell in the 3, right? The grain is the original position, which means you don't do anything. But when you activate this set of ligaments on the outside of wall, and then you inflate the 3 fingers, each finger is going to go bending inwards, and collectively they can generate this kicking motion. You can also activate the other 2, right, ligaments on each of the fingers, and then you can generate this opening, and then thus you can generate dropping manipulation. And more similarly, and on the same level of difficulty, I would see, you can activate this set of ligaments such that actually the fingers are going to move sideways, and collectively they can do twisting. So for that, actually, we are using, I mentioned that we're going to need small materials with tunable stiffness. And for that, we use this conductive propylene-based elastomer. It's a patented material based on my postdoc work at SMU. So basically, for this small material, we start with propylene acetylene copolymer elastomer, and then we add carbon black into the mix. We're gonna have this pellet form, and then because of the low melting point of the copolymer elastomer, we can easily machine it by applying heat and pressure. So we can use a heat press machine to laminate these pellets into thin film, and then use a laser engraver to pattern this into structure that we desire. So here from this step 4 to step 5, actually there's multiple step manufacturing process, which I won't elaborate on here. So this slide is some characterization of this CPBE strips. As you can see, after we apply some voltage, the modular, the stiffness or the Young's modulus of the structure will change from over 100 megapascal to roughly a few megapascal, which is roughly more than 30 times of stiffness change. And we can also characterize this, the activation time that's needed for this change. And you can see that actually roughly 10 seconds, we will be able to complete the activation if we use tens of volts as activation voltage. Now here is some demonstration of the soft gripper. You can see that we use it to pick up all sorts of objects, including ping pong ball, tape roll tape, and glass ball, some plastic pliers, clippers, and this is the petri dish. Actually, we pick up this petri dish from inside by bending outward. And there's paper packet, and also we twist this ping pong ball here. We have a video here to show this quickly. This is real time. So first we finish grasping, right? Then we turn on another set of ligaments. We can do twisting. This is sped up 4 times. Okay, that's good. That's the first approach. The second approach we developed for dynamic tunable adhesion is based on, for soft gripping is based on dynamic tunable adhesion. As noted earlier, existing approaches to adhesion tuning are mostly static. So we propose to dynamically tune adhesion through manipulation of the stiffness of the core in a core shell composite structure. Basically, Kevin Turner and Payne showed earlier that actually if you insert a rigid core into the elastomeric repose, you're going to change adhesion. Now we want to use small material to change the stiffness of the core. So when we have a rigid core, it will be having high adhesion. When we activate the core soffit, we will have lower adhesion, and that way we can pick the object up when it's rigid, and then do the manipulation and release when needed by just taking turn the switch. So small materials with tunable stiffness, like a CPBE, right? As we described earlier, are perfect candidates for the core here. We went on to implement the design, and instead of those circular shape thing, here we have rectangular cross section. This is more for convenience of fabrication. Here there's a step of fabrication, which I'm going to skip the details. You can see that actually these are experimental results. You can see that actually the draw adhesion, the composite post, all have higher draw adhesion than the pure PDMS post. And when you activate the sample using voltage, or either 20 volts, 30 volts, or 40 volts, you can see there are different level of draw adhesion tuning. And we did experiments and simulation to make sure actually for this 20 and 30 case, for the time duration we're applying, we actually apply, I would say 200 seconds. So for that time, there's not enough to fully activate the sample. Thus you see partial activation here. So that was we are certain that actually this group, when we use 40 volts, we are able to fully activate the sample. And then for this TOL ratio here, we are able to achieve 16% of original dry-adhesion strengths. That means 7 times of dry-adhesion change, which are pretty good. And we do this within a matter of seconds. So we also did finite element simulation. This is the quarter model. So this is the center of the interface. And you can see that actually when we don't do activation, right? A, B, and C, they're not activated. When we don't do activation, actually you can see there's a high stress region in the center. But if we activate this whole thing in the region in the center, there will be nothing because everything's soft, right? So you're gonna only have stress concentration at the center, at the edge, and this will promote edge crack, whereas all these will be center crack. And there's a shift of the center crack location. Here will be at center, and then in this case, when you go really TOL, really small, right? Actually, it starts somewhere between the edge and the center. So we did all this calculation in this paper, which I won't go into too much detail. These results kind of qualitatively explain why we're seeing the increased dry-adhesion from the mechanical testing results I showed earlier. Here is a quick video. So we come down, we pick it up while we don't turn on the voltage. And here we're gonna turn on the voltage at certain point. We use 80 volts here. As you can see, this is sped up by 5 times within a matter of 1 second, right? In the video, which means 5 or 6 seconds. In reality, we're gonna be able to release the object like that. Now, you might say, oh, 80 volts is too high, and 5 volts, 5 times, 5 seconds is too long. I cannot wait that much long. Actually, those are indeed the concerns which we'll address later. Another variant, I would say, a variant approach for this tunable dry-adhesion is after we did that, we asked ourselves the question: why do we have to have the core? Looking at this schematic, right? We know everything is happening at an interface, but then why do we have to activate the material here, right? If we don't activate the material here, if we just do, if we can just use a thin layer of small material, right, close to the interface, that should give us better performance in terms of activation time, right? Because instead of this huge, like U-shaped small core, we just activate a thin layer of small material right close to next to the interface, right? And we actually implement this idea, and we use aluminum alloys instead of CPBE. To kind of implement this design. These are aluminum alloys. They are alloys, right? They are much more conductive than CPBE, which make it convenient. Actually, in this sense, actually, we are trying to increase the length of these channels within this same layer to get like a measurable resistance such that we can do activation easier. The challenge here is how can you use reasonable like a battery, but don't burn it, right? Because the current can be relatively high. So, but we do recognize that the potential issue for this is, there's robustness issue, right? Because these are liquids. Whenever you deal with liquids that are melting and softening, for example, if it's in rigid form and this surface got an impact, it might just break somewhere in the channel, and then this thing cannot be used anymore. You have to do something to get it back, right? You have to melt it again, and then hope that it can be stored there. So anyway, I won't go into details about this, but I do have a quick video to show this. This is real time, and here actually we have a block of aluminum disc. You can see actually with this last small piece of elastomer, we're able to pick this almost 1 pound aluminum disc, and we apply 5 volts within roughly 1 second. Between 1 and 2 seconds, we are able to release this object, and this is real time. So we do indeed this approach. We can reduce the voltage required, which will make everything portable. And also we can reduce the time, which make it more practical in factory. Okay, the third approach we're going to talk about is based on pressurized, it's pressurized soft gripper. So approach 202A are subsurface stiffness modulation. We call it SS, and for dynamic tunable drawation. We also propose and explore subsurface pressure modulation in the NRI project. The idea is, we have been using small material to change the stress distribution on the interface. Then we wonder whether we can simply use pressure. So to verify the concept, we designed this elastomeric post containing this chamber here, and we can play with the pressure inside the chamber to release the object, essentially. Here, there's a multi-step fabrication procedure, which I won't go through the details. So here we also did this stress analysis using linear superposition principle to try to understand the contribution of different loading components to the overall stress distribution. So we look at the load applied, which is the load applied by the dead weight, the object we're trying to pick up, and also load the pressure on the inside. We break this into two parts: the pressure on the side wall and also the pressure on the top and bottom surface. And we can see that actually these different components, they contribute to different I would say stress concentrations on the interface. These are all like normalized by this one normalized by the average force, and this one normalized by the P pressure applied. And you can see actually this pressure on the side contributes the highest stress concentration on this position corresponding to the side wall. Okay, whereas this pressure on the top and bottom one, they are negative. They don't kind of wedge open the crack if there's a crack here. Okay, and this data weight here is also kind of moderate. I would say the stress concentration is only 2 times, where this can be 6 times. So and that explains the experimental results we got. Literally, we found out that actually when we start with the pressure from 0 and increase all the way, and we normalize it by the sigma 0, which is the initial strength of the device. The strength of the device, which is also normalized by the initial strength of the device, we will start from 1, right? When P equals 0, there will be sigma 0 divided by sigma 0. You're going to have 1 here. You can see when we increase the pressure, the drawation actually is going to increase a little bit and then come down sharply and then level out. The reason for that is if we combine all the stress analysis we did earlier, we can see that actually when when the input pressure is 0, we are at here this line. So there's not that much. There's a stress singularity on this tail, but here there's not that much stress concentration. When we increase the drawation, this tail, this stress concentration here is going to increase, but the stress concentration on the edge will be suppressed. That explains why we're having an increase of drawation. But very quickly, if we keep doing this, this spike will dominate, and that will introduce crack. And that explains the sharp drop of the drawation in the second stage. But of course, if you keep increasing this, this eventually is going to level out. So, from this plot, actually, we were able to say we can achieve roughly 4 times drawation change with roughly 50 kilopascal pressure input. The 4 times come from, we start from 1, and then we can, if you draw a line here, we roughly at a 0.25 when we have P equal to P sigma 0. But for all different substrates and also, with different roughness, right? We are able to measure this, quantify this to be roughly 50 kilopascal. All right, so this is a quick summary of this section on compliant robotic manipulation. We can see that actually we use this multi-finger approach, the tunable drawation approach, and also a variant form on the tunable drawation approach, and also this pressurized soft gripper. These are all recent work, I would say, but there are many open questions in this topic of compliant robotic manipulation. For example, based on knowledge learned from this customer discovery interviews with more than 100 companies all over the United States, we are able to identify that actually, for one, automotive company, right? These robotic manipulators, they are shifting away from compressed air. and vacuum cups due to energy cost consideration. So another thing is objects with curved geometry. Even think about a car, right? For a car, the windshield is relatively smooth, but there are other parts that are with a lot of curvature. So these objects have always been challenging to manipulate for all industries. So the dynamic tunable radiation approach is explored here. Both the SSM and also the SPM actually, they consume much less energy because activation is needed only for releasing. We don't do activation when we pick objects up. We only do it when we release. And also this can potentially handle objects with curved geometry. If we can, for example, if we can make the substrate kind of compliant, right? If we can turn the compliant stiffness, we can adapt better to the shape of the object and do engage and do manipulation. So for the outlook on this project, so we plan to integrate dynamic tunable radiation approaches, both SSM and also SPM, onto existing robotic grippers for universal grasping. Here there's some earlier demonstration prototype I would see for this approach. This was done by collaborator at CMU, my postdoc advisor. But this is an ongoing project. We have other efforts ongoing right now for this project. Well, with that, I'm gonna move on to the second part of this talk. We're gonna talk about novel smart materials with tunable properties and the soft robotics enabled by these novel smart materials. First, we're gonna look at the motivation and design of the smart materials. And then we talk about one application, which is active morphing drone wing design enabled by the smart materials. So when we talk about this CPBE, or LMPA for the soft gripper, right? We have been using this for the ligaments, the core, and there I mentioned that actually the CPBE activation voltage is high because its electrical conductivity is low because it has copolymer elastomer mixed with carbon black, right? Carbon black is not that conductive. And because of the size of the additions, right? The carbon black additions, the minimization for this structure is also very challenging because the carbon black particle can easily go to roughly 50 micron big. Then the size of that actually limits how thin you can go, all right, using CPBE. We also did actually other approaches for these smart materials for stiffness tuning. This is one work done by me actually at CMU. We were using multi-layered composite to containing LMPA layer for large stiffness tuning. But this structure turned out to be not robust. As you can tell, this is literally a multi-layer structure, and there's this is top view. You can see the soft feeder channel here made of gallium. The issue with this is literally robustness. When you stretch it, you can stretch it a lot, but then it's hard for it to go back to the original shape, given that the elastomer we're using, and also this is a huge, this is literally a reservoir of fused metal. Once it melts, it's hard to go back to its original shape because it's very heavy, and this is just a block of the small material. So there are also other approaches using internal heating for addition, which are not practical. For example, this one actually is done by Robert Shepard group at Cornell. They literally did this elastomer foam first, and they try to infiltrate LMPA into the pores of the elastomer foam. And they claim it to be continuous bi-continuous foam, but from the result, they showed actually, we would argue that actually seems like all these particles are not that well connected, and they have to use internal heating for its activation. So this all motivated us to engineer and design, better smart materials to fit the needs of all sorts of soft robotic applications. Along the same line, actually, almost in parallel, there have been efforts on soft electronics. So the smart material we talked about earlier is using tunable stiffness. But these ones, they're not training stiffness, but they are soft and stretchable, and they're conductive. So you can, this is mainly to replace the silicon electronics. So these are efforts done by the CMU group. And you can see they use aluminum alloy like inks. Either they have channels like this, and they use a laser engraver or thing. They can do this soft electronic devices. And more recently, they also the CME group actually also did this. They mix LMPA particles or droplets into a elastomer matrix, and they're able to make this composite like this. So this composite is not conductive, right out of the manufacturing process, but they can use some sharp object to scratch the material. Sorry, scratch the material, and then you can literally rupture these little droplets and make a conductive pathway. And this way, they claim you can do selectively create conductive pathways, and that way you can do soft electronics. And this indeed, once they make the pathway, it's pretty conductive because it's all like aluminum alloy droplets, and literally their alloys connect together. So pretty cool stuff. Now, to design robust smart materials with large stiffness change, here I propose a foam matrix composite with LMPA as foam phase. So we're gonna start with this LMPA foam to make sure the LMPA is well connected. And then we're gonna infiltrate this foam with elastomer. And this way, the material is gonna be indeed bicontinuous. It will be very robust because we have this outside, elastomer matrix, and it will be really rigid before activation because this foam, the LMPA foam is gonna bearing all the load, mechanical load when it's not activated. But when you activate this whole thing, right, you literally have a PDMS containing liquids inside, liquid alloy inside, and this material will be very soft. And as you can imagine, we can do hundreds of times difference in stiffness, and these are have been verified by experiments. But it is also very robust. But the problem is that this is too conductive to be activated directly. The electrical resistance is literally 0. You cannot activate this by dual heating through the composite itself. You have to do external heating, which means you can wrap around a heater actually to do activation. So I'm gonna talk about one application based on this material when we get there roughly in 10 slides. Okay, so to design smart materials with tunable electrical conductivity, I then propose adding conductive fibers into the particle matrix composite to connect the dots. So for one implementation, we used nickel-coated carbon fibers. So this is a schematic of a 2-component composite, which is non-conductive as evidenced by many previous studies. We're trying to add this nickel-coated carbon fiber, which are highly conductive, because carbon fiber itself is conductive and then is coated by nickel. So this NCCF fibers, they will serve as bridges between these highly conductive LMPA particles. And together, they're gonna generate this 3-component conductive composite, and you can do selective activation here. So I have one beam here, I can run current through this portion, and we can activate this portion, while this portion is still being not activated. So we actually did a calculation of this smart composite, and this is a stress strain plot. Here we used effective medium estimation to characterize the stiffness change. As you can see, we are able to achieve roughly 20 times of stiffness change for this composite when we vary the volume fraction this way. We also used modeling effective medium theory. Actually, this is done by Professor Yang Jiao to estimate the electrical conductivity of the composite. As you can see, we here in this plot, we have both experiments and theory. So the experiments are field markers and theory are open markers here. You can see that actually for the 3-component composite, it's very interesting that actually this conductive one it doesn't change with time. Its electroconductivity doesn't change with time. We don't exactly know why this is the case. The simulation actually doesn't consider temperature dependence because of the lack of data for the nickel coating carbon fiber. So which means for both cases, right, you don't have much change here. But we can see for in the experiments for this other three-component composite, the electrical resistivity actually changed a lot when we increase the temperature. So we figured that we might be sitting at this the percolation threshold when we play with the volume fraction. Clearly, there's a lot of to investigate here, and we are trying to do that actually together. Here's a quick demo of this some material. In this case, we use a relatively low power supply, power rate. This was sped up 5 times. You can see after roughly 1 minute or something, we are able to soften this part. We also changed the can you put down this for a second? Can you put them on? Put them on. I'll take this. Okay. I'm gonna play the video actually. Sorry. Okay. So this one we increased the power input. This one actually we slowed down. We slow down video. And you can see within a few seconds, actually, within a few seconds, this activation has been finished. Can you go to mom actually? Sorry guys, my daughter is trying to interfere with. Can you go to mom actually? Finish, okay. Yeah, so this videos demonstrate that actually this the much better property than previous smart materials. It has tunable stiffness, roughly 30 times, 20 times, 30 times. But at the same time, its electrical conductivity can be tuned. And now we have evidence. We show that actually we can activate this these samples using lithium-ion battery. With a few volts. This has never been demonstrated before. But clearly, we haven't, this is about the future work along this line. We haven't even tried to optimize the design yet. So this is the 3-component particle fiber matrix component system that, can be tuned much, whose property actually still needs to be explored. So the modeling of such composites, we are actually working with Yang and Max here at ASU. We aim to achieve closed feedback loop between the simulation and also experiments to fully explore the design space, which include the volume fractions, the volume fraction, the shape, the aspect ratio of the fibers, the conductivity of the particles, all the things, we still need to fully explore this space. We also want to kind of change, the elastomers. For example, PDMS is not ideal elastomer, I would say, because of the certain mechanical properties, especially for fracture fatigue. We also want to explore other conductive fibers, such as soft ones, especially this low melting point alloy. If we can make low melting point alloy fibers, the interaction between the fibers and the particle will be very intuitive to investigate. We would like to study the fracture fatigue behaviors of these composites under extreme conditions, for example, during activation. Now, application of this smart material, right? Now, with this normal smart material, we can immediately apply them on background all the software papers I've been talking about, and this will enable faster activation, lower voltage required, and also minimization will be possible given all the benefits we're getting from this new novel small materials. Here I'm going to talk about one example, which is active drone wing design actually. So we use the LMPA foam composite to design multiple tunable joints in one drone wing here. And we then use a tandem-based approach to try to control the shape of the drone wing by applying a torque through electromotor. So we also propose to use adaptive control and also reinforcement learning to learn the fluid dynamics and try to come up with better control algorithm to dynamically tune the drone wing shape to achieve higher efficiency. This is in collaboration with Professor Hao Xu and Professor Yan Gu at UMass Lowell. There are also other recent ongoing projects. For one, this one here is crawling robot made of a composite structure, elastomer, elastomer thin films embedded with nylon wire, which is also a composite structure, right? So we can send pulse of energy or heat to the from a microcontroller, right, to a battery, microcontroller battery, to the nylon wire here, and then due to the phase change, there will be instantaneous like a locomotion or shift change out of this nylon wires, and then collectively you can design this soft crawling robot. We also are trying to design robotic needle with large curvature maneuvers using the novel small material developed. This one, yeah, we don't have time to talk about in detail. So with that, I'm going to conclude. I think in terms of time, it's perfect. So I'm going to conclude and provide acknowledgements for all the work. So we identify the interdisciplinary research theme in smart, hybrid, active, and nature-inspired materials, mechanics, and machines for better human-machine environment interactions. And we then look at compliant robotic manipulation approaches, integrating small materials and solid mechanics. The future work on this, we kind of briefly discussed. We also look at novel small materials with tunable properties, and together with the potential application of them, including active morphing drone wing design, among others. So once again, this is the where we have been trying to do our work using material engineering, solid mechanics, learning, which I didn't touch on, but there are some other projects. Actually, we have been doing that. Similar science and computer vision, try to impact or try to improve human-machine environment interactions. With that, I'm going to provide acknowledgements. All this work was have not been possible without support from my peer advisor, postdoc advisor, and also my collaborator mentor, Kevin at UPenn. And also, I would like to thank all other collaborators, including Yang and Max here, and also Hao and Yan and Teng here at SMU, among others. And also my students, Amir, and Adarsh, Silvash, Shai, and other students, etc. Last but not least, I would like to acknowledge the support from the funding support from DAPA for my postdoc work, and also ASF, UNR, and DOD, UNR, and ASU for the funding support. With that, I'm gonna thank you for your attention. I'll be happy to take any questions. Thank you.